All right, and welcome back to BME 2315. Today we're going to be talking about numerical differentiation. So, robotic surgery has advanced tremendously in the past few years, and while there are many different pieces of instrumentation and sensors on these things, one of the main things that are used by these robotic arms are accelerometers. And so accelerometers are ways of detecting that acceleration based on the acceleration of these tips, and then it can do these instruments are doing a numerical differentiation and integration to then figure out and relate the velocities, positions, and accelerations of the various components. And so in this way, something that you know very well from calculus 1, about integration and differentiation is intrinsic to how these robotic arms perform. And this is a really neat little video showing a robotic surgery on a grape. I encourage you to use it down. Take a look at the YouTube video down there. So this is a motivating topic for us in this section, because we're going to be looking at how to perform this sort of numerical differentiation on the computer, even if we don't know a function f. In calc class, you always were given the function f, but we're going to learn that we can perform differentiation even if they're just data points, for example, from a robotic arm. So the learning goals for this section are to understand how Taylor series can be extended to approximate the derivative of functions and take derivatives of data. And also, we're learning a general concept that applies to many different other types of algorithms, which is we're learning that you can improve accuracy or to decrease truncation error by either decreasing the step size or increasing the numerical order of the method. So let's start out with something rather simple. Let's say if you only knew the values of your function at 3 points, at x equals 0, at 1.2, at x equals 0.5, and at x equals 1, so a y value of 0.2, if we only had those values, how would you estimate the derivative of f if you didn't know the underlying blue function? Well, one way that would be simple would be to take this slope right here, to connect the point at 1 to the point 5. And so that would be what we call a forward approximation, right? And so we'd be saying f of 1 minus f of 0.5, and that would be the rise, and the run would be the x values, so 1 minus 0.5. And if we could plug in the values that we see there, we'd see that this would be negative 0.725 over 0.5 to give us an estimated slope of negative 1.45. Another approach would be to take a backward approximation, which is to use this point and this point right here. So I'm going to draw a line that goes here. Let me make that a little bit closer. There we go. That's more precise. To kind of take the slope of this line that connects the first point and the second point. So that would be what we call a backward approximation, where we're taking the f of 0.5 minus the f at 0, and we're subtracting 0.5 minus 1. And from that, we get an estimated slope of negative 0.55. That's a fairly different approximation of the derivative at this location, isn't it? And finally, there's one other approach that we might take called the centered approach. And in this case, rather than taking this value, you could look at the very first point and the very last point and look at the slope connecting those two. And so that is now centered around the original point that we want to know the derivative at. So this would be f of 1 minus f0, and notice that's 1 minus 0 because we're the line goes the whole way across, and so that is given by negative 1 over 1, or a slope of negative 1. Okay, as you can see, the actual analytical solution to this problem is negative 9.9, so that the centered one gave the most accurate answers. So those are just kind of shorthand, three different ways of doing this without really using the Taylor series approximation. And so now we're going to look at how you can actually derive these types of functions more rigorously. So the first thing I want to do is remind you of the Taylor series. We derived this in the last class, where this was predicting the next value of a function given the current value of that function plus derivatives of these functions. We're going to be reusing this equation quite a lot, and so we're going to call that equation 1. Okay. And so notice that if we wanted to have an equation for the f prime, all we'd have to do is rearrange this equation. So let's rearrange 1. Right, so we get f prime of xi and here would be dividing through by h, because this f prime term originally had an h in it. And then we're going to ignore or not specifically define the higher order parameters. Instead, we're going to say that that is on the order of h squared, because this is a first order approximation. Then this is on the order of h squared, but we need to divide by the h as well. Okay, and so order of h squared divided by h is the same thing as order of h. Okay, so this gives us our first order forward differentiation formula. And you can also use a similar approach to estimate the second derivative of f. And so what we're going to do here is play a trick, and we're going to plug in 2h for h into equation 1. Okay, so we're going to call this equation 2. So this is f of xi plus 2 now, because we're going to be jumping 2 steps, and this is given by f of xi plus 2 times f prime of xi h, because this is h times 2, plus 2 times f of xi h squared, and notice this is 2 because we had a h squared, so it's like 2h squared became 4h, and so 4h divided by 2 was 2. And then what's left is going to be on the order of h cubed. Okay, and so we're going to call this equation 2. And so then if we take equation 2 minus 2 times equation 1, let's see what we get here. So we're going to start with equation 2, and we have f of xi plus 2 minus, this is where we're subtracting off of the first equation, so minus xi plus 1 equals negative f of xi, and it was negative f of xi because it had f of xi minus 2 times f of xi. So that would be negative f of xi plus, and then note here that the f prime terms are going to cancel out. And that's because we had 2 times f double prime minus 2 times f double prime. And so these just cancel out. And so what's left is the double prime f of xi squared, h squared. And so the error is on the order of h cubed. And so we can now rearrange this. And we're going to rearrange this for f double prime. And we get that we have a numerical approximation now for the second derivative of a function, and it's given by f of xi plus 2 minus 2 f of xi plus 1 plus f of xi. And the denominator we have h squared. And overall, this is on, because we're dividing through by the h squared, this was o to the h cubed, but then divided by h squared, because we divided through by h squared, this is on the order of h. Okay, so this gave us a nice little formula for computing the second derivative of a function when we don't even know the function itself. We can just compute from data points right there. Okay, so that's the first derivative and second derivative. We can also use a similar approach for backward or centered derivatives that use the current value and the previous value. That's what the backward is. And so the trick for the backward first derivative is that we're going to plug in minus h everywhere we had h in equation 1. Okay, and so if we do that, first the Taylor series for this would be f xi minus 1, because a negative step now, equals f of xi minus f prime xi h. Notice this is a negative because this was when we replaced h with negative h. And then plus f prime squared, or f prime, sorry, times h squared over 2. Okay, and we're going to call this equation 3. So we'll be using that in the future. And so now we can rearrange for f prime. And we get that f prime of xi equals f of xi minus f of x I minus 1 divided by h, and the error is on the order of h. So notice how this is very similar to the forward approach, but we're using x of I and x of I minus 1 rather than xi plus 1 and xi. Okay, and then finally the centered divided difference formula. So the basic idea is we're going to be subtract the forward and backward Taylor series. Okay, so we're basically taking equation 1 and we're going to subtract equation 3. That's why it was important to keep track of what we were working with. And so that gives us f of xi plus 1 from equation 1, and from equation 3 is f of xi minus 1. Okay. And then notice the zero order terms are the same, so that cancels out. And we're left with, right, so the f of xi term canceled out, and then we've got 2 times f prime xi right, and that happened because the original Taylor series has a f prime xi and then we were subtracting a negative f prime xi. So that's why we're left with 2 times that. And then notice here that we don't have the first term because f of xi canceled out. Okay. And then also the f double prime cancels out because this is the same. This f double prime term is the same in the forward and backward version of the Taylor series. Okay, so I'm going to write here that the f double prime canceled out. And so we're left with the third order term, so 2 times f triple prime xi h cubed divided by 3, and so on. And so now, remember what we're going for here is an equation for f prime. So we will rearrange itself for f prime okay, and so when we do that, we're going to end up with a f of xi plus 1 minus f of xi minus 1 divided by 2 times the step size h. And the error on that was on the order of h cubed divided by 2h. We had divided through by this, and so that would be on the order of h squared. So the really important result to notice here is that the centered divided difference formula has an error on the order of h squared, which is going to be smaller than the error from the backward divided difference formula, which is on the order of h. Okay, so far we've been taking just the first order terms and seeing what we can do with them. One of the ways to decrease truncation error is to take small step sizes, but another one is to take increasing terms from the Taylor series. And so we're going to look at how we can use that to improve the accuracy of our predictions, to make the errors even smaller. So from slide 4, we knew that f prime of xi equals, this was just our forward divided difference of approximation, was that f prime was given by this difference, and we didn't always write it out, but the higher order term that's left from this is xi plus h divided by 2, and then plus on the order of h squared. Okay, and then so what we're going to do is we're going to take this formula and we're going to substitute in the double or second derivative from slide 4. So let me just show you where that was. So this right here, this f double prime equation right here, we're going to substitute that in wherever we had where we have this f double prime in the equation here. Okay, so everything towards the left is going to be the same. Okay, and we're going to be subtracting minus f of xi plus 2 minus 2f of xi plus 1 plus f of xi divided by 2h, and this is going to be on the order of h squared. Okay, and so notice now we've got h in the denominator, 2h in this denominator, and so let me just change the colors really quick to say that then we'd just multiply these so that they can be combined. And simplify this down a bit. So we find that f of xi is given by negative f of xi plus 2 plus 4 f of xi plus 1 minus 3 f of xi. So we had and the denominator is still 2h, and the error is on the order of h squared. So the main result here is that we've got a forward difference approximation of the derivative that uses 3 points of information here rather than just 2, and that enabled us to have a smaller error. The order is on the order of h squared rather than on the order of h as it was before. Okay, so now that we've done these derivations, we're going to look at how to apply this again back at the original derivations that we had. And so we're going to compute the derivative several different ways and then compare what sort of results that we get. So first off, the one that we already did was the forward approximation. So we said if the step size is 0.5, then f prime at x equals 0.5, we said was negative 1.45. We kind of guessed at that equation right off the bat. Now for a second order approximation, so that would be using information at this point, and this point. So it's using more information going forward. It's a forward approximation. That would be what's called an and order equals 2, we'd say that f prime 0.5 is given by negative f of x plus 2 I plus 2, which is 1.5, plus 4 f of x I plus 1, and that's given as 1.0 minus 3 f of xi, which is at 0.5. So something that I think I may not have explained correctly is that because the step size is h, 0.5, the points that it would be using would be xi plus 1, and then the xi plus 2 would be at an x equals 1.5. Okay, and then all of that would be 2h. Okay, and then if you calculate what that equals, it should be around negative 0.66. Okay, and then finally we've got a difference formula, or centered formula, which is on a n equals 1. Oh, I'm sorry, we're not doing centered here. We're doing the a smaller step size. We're looking at what happens if you take a smaller step size. That's having the step sizes described above. So we're saying a first order method, but using a smaller step size. Okay, so now we're allowed to use this information. We're looking at this right here. So that equals f prime at 0.5 is estimated as f of 0.075 minus f of 0.5 divided by 0.25 now, because that's we've got a smaller step size, and that equals negative 1.15. Okay, so what we see is that in this case, the smaller step size method is the one that gave us the best results. It was better than both a larger step size, and it was also better than taking a higher order method. That won't always be the case. It's going to be problem specific. Okay, so to summarize this section, we've looked at how divided difference approximations can be used to approximate derivatives, even when we don't know f prime of x analytically. Notice in this last one, I show the analytical solution, but we didn't actually even need to know what that equation was. All we needed to know was the value of a few different data points. We learned that forward, backward, and center divided difference approximations can all be made and have various different accuracies, and so which one you choose depends on the information that you have available. And finally, we'll see that this is a general theme across many methods. The error in computation, this truncation error that we're talking about, there's two main ways to decrease it. One is to decrease the step size h, and the other one is to use higher order approximations, use those f double prime and f triple prime terms in the Taylor series. So thanks for being here, and I hope that was useful to you. Bye.